So this is a talk about what we learned in 1.5 years of running Postgres as a managed service on Kubernetes. Delivered to you in less than 10 minutes. My name is Oleksii. I'm a cloud engineer at Timescale. And at Timescale, we have a very strong opinion that Postgres is the most advanced open source database in the world. And we want to make it even better. So we create a free and open extension to work with time series data in Postgres. We deliver some abstractions like a hyper table, which basically looks like a Postgres table, but allows you to store huge amount of time series data. And we provide a way to distribute that table over multiple nodes in a form of distributed hypertables. And we make Postgres faster working with time series by doing multiple performance improvements. And this is free and this is open and you can use it on your system. But if you don't want to set it up and want to deliver us the responsibility of managing your time series data, we could do this as well because we have a Timescale cloud. It's an it's a hosting service, and the best part of it, it runs on Kubernetes. So I want to tell you first about the architecture of Timescale Cloud, so that I will come to the main topic of this talk. This is the challenges that we came across by running Timescale on Kubernetes. So the architecture, this is some screens of what it looks like from the user point of view. You create the instances of Timescale, we call them services. You can create a service of only one instance, or you can create so-called multi-node with multiple instances, and you can deliver different parameters that you set up this service. You can customize CPU, you can customize memory. One of the greatest benefits of Kubernetes is that it allows us to slice your resources the way we like. You're not limited to a virtual machine. You can set up any combinations of resources. And this is how it looks like from the internal points of view. So we use the operator pattern to reconcile the Timescale custom resource with the Kubernetes objects. And in Kubernetes, we have a stateful set. The stateful set runs multiple pods. In each pod, we have several containers. A container runs Postgres, managed by Patroni, a Postgres failover manager that talks directly to Kubernetes and updates an endpoint. We have another sidecar that runs pgback rest, allowing us to back up Postgres, not just one time, but continuously. And we can use that to restore your Postgres instance to any point in time. Basically, if anything happens with your cluster, if you lose a volume, or if you lose a pod, we can restore it right away, and we can also use it to create a new service, a clone of the existing one with the same data. And we are not limited to just the operator. The operator is mostly stateless, but we also have a stateful service called the deployer. The deployer task is to create this Timescale DB object, and the deployer is also responsible for monitoring the service while it's running and delivering us information in form of monitoring graphs and in form of alerts. So that is the way how we deploy the service on Kubernetes. And now I am going to transition to the main kind of greatest hits of our challenges. So what we came across. For instance, Postgres has some assumptions. What happens if it runs out of memory? And there's a sane assumption. If you run out of memory, you want to get an error. What happens on Kubernetes is instead of getting an error, there is such a thing as out-of-memory killer. The out-of-memory killer comes and kills your process. You don't want to do that if you are a stateful service. If your backend, if your Postgres backend, Postgres multi-process system, if your Postgres backend is killed, everything has to be restarted and your query is interrupted. But if that out-of-memory killer chooses the main process, the postmaster, Postgres just crashes, and if it crashes, it may not even start afterwards, so you have to clean up after that. And how do people overcome that? You can tune Linux system to actually set your memory overcommit to a certain settings that said never go beyond the limit of your system. Alas, in Kubernetes, it's not available. In Kubernetes, this is not possible to set on a cgroup level, only on the node level, and there are very strong reasons why you cannot set it on the node, because your node typically runs other processes. And there is a ticket created by one of the community members listing all these issues. Well, the ticket has been just closed because of lack of interest from other people. So if you are watching this talk and interested in that topic, please go there and try to reopen the ticket. How did we actually solve this problem? Well, Linux has a function called malloc that is used to allocate memory. And what we are doing is overriding malloc with our own implementation. And what our implementation is doing is basically doing internal accounting based on pod limits and based on some operating system kind of offsetting some operating system data. And when we find out that the next allocation will go over that limit, instead of letting it go and letting the out-of-memory killer kill your pods, kill your processes, we return null as if your system becomes as if your system behaves in a reasonable way. And that is how we this is how we solve the out-of-memory. But wait, this is not all. When running stateful workload, we want fewer downtimes. If your database is down because you want to upgrade to a new version of software, customers are unhappy, and we run managed service. We want to make customers happy. So what we are doing for that, when you update a software, typically when, for instance, you update your extensions, and we release new version of Timescale extension every month, you normally replace your Docker image. But that doesn't work because replacing your Docker image is a pod downtime. So instead, we created a special program that runs inside your container. And that program gets the new version of extensions from S3. Those are kind of bundles that contain binary files together with checksums. So this is copied to the container, to the special area in the persistent volume, so it survives the container restart. And then this is symlinked into the place where Postgres expects to find binaries. So you deliver a new version of your extension transparently without restarting the container. The best part of it, we are Postgres people. So how do we run this program? We run this program by connecting to database and using copy to program. This is a special command in Postgres that allows you to copy data from any program to your database. But we don't need any data. We need just to launch this software. So instead, what we are doing is copying empty data just to launch this program. So this is how we avoid downtimes. And it would be ideal if we could solve this in a way that is beneficial to other members, if Kubernetes provides us kind of a mutable area inside the pod. But this is kind of our wish list. So another challenge, you all know that Kubernetes is powered by Kubernetes masters. Inside there is etcd storing metadata, and etcd is like 5, 7, or sometimes 3 nodes, so it's distributed. It's supposed to last. It's supposed not to die all nodes at the same time. However, what happens is your cluster can have a degraded performance. If, for instance, you created a lot of objects in your cluster, or you made a mistake and your cluster is full of error logs, or if your volume support in Kubernetes is not performing correctly, those things can degrade etcd performance up to a point where your cluster becomes inaccessible. And because inside Kubernetes we also run patroni inside the pod, which talks to Kubernetes API to determine who of the Postgres nodes is the leader node, who can accept writes. And if Kubernetes API is not available, patroni can also not get this information and just goes to read-only mode. And all your data becomes read-only. This is not good. So we are getting around this by introducing a special patroni static primary mode. In that static primary mode, patroni will not, when you have only one pod, when you don't have replicas, you know that you definitely have only one leader, and patroni does not go into read-only when the patroni does not go in read-only when primaries are not available. So this is how we solve this problem. Of course, we would like etcd to be more accessible in terms of health monitoring, and we would like to avoid these problems when etcd is down, because it's a huge pain for other parts of the Kubernetes cluster. So better observability, better fire drills, better support in Kubernetes. AWS bugs, sometimes vendor bugs spill into the Kubernetes platform. We run our services on AWS, and we came across a problem when we tried to provide customers large volumes, those that are 1 terabyte and more. We found out that Postgres did not deliver, AWS did not deliver those volumes with random data. It delivered something that looked like an already partition table. Partition table from Atari. This is Atari. You probably need hundreds of them to run every Kubernetes microservice. However, Kubernetes refused to format them, and pod was stuck at startup. So what we did is we used Kubernetes volume snapshots, so you can take your volume, snapshot it, and use a snapshot to create another volume. We created a very small 1 gigabyte volume, snapshotted it, and then from that snapshot created a bigger volume. The volume can resize itself automatically. However, it cannot resize its file system, because the file system, you have to do it on your own. So we created an init container to do that. This is luckily has been fixed by AWS, but the point of that is that you will get bugs in your cloud provider, and you would have to work around them. So the volume resize, you can shrink you can upsize your volume, but you cannot shrink it. Neither AWS nor Kubernetes support that. But Timescale has a compression built in. So if you ingest your time series data, and then after ingesting you compressed it, you find out that you have a huge volume that you pay for, but you don't need it. Alas, you cannot shrink your volume afterwards. So what we did instead, we created a fork of the service. I mentioned before that we have a backup on S3, which contains the base backup plus all the changes. So we used all that to create basically a copy of your service, but the copy does not have to run the same resources. So it can have a different CPU memory, but it can also have a smaller disk. So with that, your fork can run the same data as your original service, but has a smaller volume. So if you can switch to that, you will not pay more for what you don't need. Basically, that is it. Thank you very much for listening, and always be launching. If you have any questions to me, then you can ask me on Twitter. You can ask me on email. If you come to KubeCon, there will be a Timescale booth on KubeCon, so you're welcome to come and also talk to me in person. And if you go to the Data and Kubernetes community, you can also meet me in the evening during the event. Thank you.